Newton's first law of motion. Newton built on Galileo's ideas and laid the foundation of mechanics. In terms of 3 laws of motion that go by his name. Galileo's law of inertia was his starting point, which he formulated as the first law of motion. Every body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. The state of rest or uniform linear motion both imply zero acceleration. The first law of motion can therefore be simply expressed as: if the net external force on a body is zero, its acceleration is zero. Acceleration can be non-zero only if there is a net external force on the body. Examples of first law of motion, Part 1. In some examples, we know that the net external force on the object is zero. In that case, we can conclude that the acceleration of the object is zero. For example, a spaceship out in the interstellar space, far from all the other objects, and with all its rockets turned off, has no net external force acting on it. Its acceleration according to the first law must be zero. If it is in motion, it must continue to move with a uniform velocity. If we know that an object is unaccelerated, that is, it is either at rest or in uniform linear motion, we can infer from the first law that the net external force on the object must be zero. Gravity is everywhere. For terrestrial phenomena in particular, every object experiences gravitational force due to the Earth. Also, objects in motion generally experience friction, viscous drag, etc. If then on Earth an object is at rest or in uniform linear motion, it is not because there are no forces acting on it, but because the various external forces cancel out, that is, add up to zero net external force. Examples of first law of motion, Part 2. Consider a book at rest on a horizontal surface. It is subject to 2 external forces. The force due to gravity that is, its weight W acting downward, and the upward force on the book by the table, the normal force R. R is a self-adjusting force. Here, the forces are not quite known fully, but the state of motion is known. We observe the book to be at rest. Therefore, we conclude from the first law that the magnitude of R equals to that of W. A statement often encountered is, since W is equal to R, forces cancel and therefore the book is at rest. This is incorrect reasoning. The correct statement is, since the book is observed to be at rest, the net external force on it must be zero. According to the first law, this implies that the normal force R must be equal and opposite to the weight W. Examples of first law of motion, Part 3. Consider the motion of a car starting from rest, picking up speed and then moving on a smooth straight road with uniform speed. When the car is stationary, there is no net force acting on it. During pickup, it accelerates. This must happen due to a net external force. Note, it has to be an external force. The acceleration of the car cannot be accounted for by any internal force. This might sound surprising, but it is true. The only conceivable external force along the road is the force of friction. It is the frictional force that accelerates the car as a whole. When the car moves with constant velocity, there is no net external force. If a car or a bus suddenly starts moving, a person sitting in it would fall in the backward direction. This is because the lower part of the body of the person is in contact with the seat of the bus and is carried forward by the motion of the bus. But the upper free part of the body of the person remains at rest due to inertia, and so the person falls in the backward direction. But if the moving bus suddenly stops, the person falls forward. When the bus suddenly stops, the velocity of the lower part of the body reduces to zero, but the upper part of the body still has the velocity of the bus. Hence, the person falls forward. Examples of first law of motion, Part 4. An example based on the above topic. An astronaut accidentally gets separated out of his small spaceship accelerating in interstellar space at a constant rate of 100 meters second raised to the power minus 2. What is the acceleration of the astronaut the instant after he is outside the spaceship? Assume that there are no nearby stars to exert gravitational force on him. Since there are no nearby stars to exert gravitational force on him, and the small spaceship exerts negligible gravitational attraction on him, the net force acting on the astronaut once he is out of the spaceship is 0. By the first law of motion, the acceleration of the astronaut is 0. Newton's third law of motion, part 1. Consider a pair of bodies A and B. B gives rise to an external force on A. A natural question is, does A in turn give rise to an external force on B? In some examples, the answer seems clear. If you press a coiled spring, the spring is compressed by the force of your hand. The compressed spring in turn exerts a force on your hand, and you can feel it. But what if the bodies are not in contact? The earth pulls an apple downwards due to gravity. Does the apple exert a force on the earth? The answer is not obvious since we hardly see the effect of the apple on the earth. But the answer, according to Newton, is yes. The apple does exert an equal and opposite force on the earth. We do not notice it since the earth is very massive. And the effect of a small force on its motion is negligible. Thus, according to Newtonian mechanics, force never occurs singly in nature. Force is the mutual interaction between two bodies. Forces always occur in pairs. Further, the mutual forces between two bodies are always equal and opposite. This idea was expressed by Newton in the form of the third law of motion. To every action, there is always an equal and opposite reaction. Newton's third law of motion, part 2. The terms action and reaction in the third law mean nothing else but force. A simple and clear way of stating the third law is as follows. Forces always occur in pairs. Force on a body A by B is equal and opposite to the force on the body B by A. The terms action and reaction may give a wrong impression that action comes before reaction, that is, action is the cause and reaction the effect. There is no cause-effect relation implied in the third law. The force on A by B and the force on B by A act at the same instant. By the same reasoning, any one of them may be called action and the other reaction. Action and reaction forces act on different bodies, not on the same body. Consider a pair of bodies A and B. According to the third law, FAB is equal to FBA. That is, force on A by B is equal to force on B by A. Thus, if we are considering the motion of any one body, A or B, only one of the two forces is relevant. It is an error to add up the two forces and claim that the net force is zero. However, if you are considering the system of two bodies as a whole, FAB and FBA are internal forces of the system A plus B. They add up to give a null force. Internal forces in a body or a system of particles thus cancel away in pairs. This is an important fact that enables the second law to be applicable to a body or a system of particles. Momentum and Newton's second law of motion. Part 1. Momentum of a body is defined to be the product of its mass m and velocity v, and is denoted by P. P is equal to mv. Momentum is a vector quantity. Let us now take some examples which will illustrate the importance of momentum. Suppose a lightweight vehicle, say a small car, and a heavyweight vehicle, say a loaded truck, are parked on a horizontal road. We all know that a much greater force is needed to push the truck than the car to bring them to the same speed in the same time. Similarly, a great opposing force is needed to stop a heavy body than a light body in the same time, if they are moving with the same speed. If two stones, one light and the other heavy, are dropped from the top of a building, a person on the ground will find it easier to catch the light stone than the heavy stone. The mass of a body is thus an important parameter that determines the effect of force on its motion. Momentum and Newton's second law of motion. Part 2. For a given mass, the greater the speed, greater is the opposing force needed to stop the body in a certain time. Taken together, the product of mass and velocity, that is, momentum, is evidently a relevant variable of motion. The greater the change in the momentum in a given time, the greater is the force that needs to be applied. A seasoned cricketer catches a cricket ball coming in with great speed far more easily than a novice, who can hurt his hands in the act. Reason is that the cricketer allows a longer time for his hands to stop the ball. He draws the hands backward in the act of catching the ball. The novice, on the other hand, keeps his hands fixed and tries to catch the ball almost instantly. He needs to provide a much greater force to stop the ball instantly. The conclusion is clear. Force not only depends on the change in momentum, but also on how fast the change is brought about. The same change in momentum brought about in a shorter time needs a greater applied force. In short, the greater the rate of change of momentum, the greater is force. Suppose a fixed force is applied for a certain interval of time on two bodies of different masses initially at rest. The lighter body picks up a greater speed than the heavier body. However, at the end of the time interval, observations show that each body acquires the same momentum. Thus, the same force for the same time causes the same change in momentum for different bodies. Momentum and Newton's second law of motion. Part 3. In many cases, the momentum and change in momentum both have the same direction. But this is not always the case. Suppose a stone is rotated with uniform speed in a horizontal plane by means of a string. The magnitude of momentum is fixed, but its direction changes. A force is needed to cause this change in momentum vector. This force is provided by our hand through the string. Our hand needs to exert a greater force if the stone is rotated at greater speed, or in a circle of smaller radius, or both. This corresponds to greater acceleration, or equivalently, a greater rate of change in momentum vector. This suggests that the greater the rate of change in momentum vector, the greater is the force applied. These qualitative observations lead to the second law of motion expressed by Newton as follows. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. F is proportional to delta mv by t. The second law can also be written as F is equal to kma, which shows that force is proportional to the product of mass m and acceleration a. For simplicity, we choose k is equal to 1. The second law then is F is equal to ma. The second law of motion given by is applicable to a single point particle. In SI unit, force is 1. That causes an acceleration of 1 meter by second square to a mass of 1 kg. This unit is known as Newton. 1 N is equal to 1 kg meter per second square. If a force is not parallel to the velocity of the body, but makes some angle with it, it changes only the component of velocity along the direction of force. The component of velocity normal to the force remains unchanged. Impulse. We sometimes encounter examples where a large force acts for a very short duration, producing a finite change in momentum of the body. For example, when a ball hits a wall and bounces back, the force on the ball by the wall acts for a very short time when the two are in contact. Yet, the force is large enough to reverse the momentum of the ball. Often in these situations, the force and the time duration are difficult to ascertain separately. However, the product of force and time, which is the change in momentum of the body, remains a measurable quantity. This product is called impulse. Impulse is equal to force into time duration is equal to F into delta t is equal to change in momentum. A large force acting for a short time to produce a finite change in momentum is called an impulsive force. Conservation of momentum. Part 1. The second and third laws of motion lead to an important consequence, the law of conservation of momentum. Let's take a familiar example. A bullet is fired from a gun. If the force on the bullet by the gun is F, the force on the gun by the bullet is minus F, according to the third law. The two forces act for a common interval of time, delta t. According to the second law, force delta t is the change in momentum of the bullet and minus F delta t is the change in momentum of the gun. Since initially both are at rest, the change in momentum equals the final momentum for each. Thus, if Pb is the momentum of the bullet after firing and Pg is the recoil momentum of the gun, Pg is equal to minus Pb, that is, Pb plus Pg is equal to 0. That is, the total momentum of the bullet plus gun system is conserved. Thus, in an isolated system, that is, a system with no external force, mutual forces between pairs of particles in the system can cause momentum change in individual particles. But since the mutual forces for each pair are equal and opposite, the momentum changes cancel in pairs and the total momentum remains unchanged. This fact is known as the law of conservation of momentum. The total momentum of an isolated system of interacting particles is conserved. Conservation of momentum. Part 2. An important example of the application of the law of conservation of momentum is the collision of two bodies. Consider two bodies A and B with initial momenta PA and PB. The bodies collide, get apart with final momenta PA prime and PB prime respectively. By the second law, FAB delta t is equal to PA prime minus PA and FBA delta t is equal to PB prime minus PB, where we have taken delta t, a common interval of time for both the forces, that is, the time for which the two bodies are in contact. Since FAB is equal to minus FBA by the third law, PA prime minus PA is equal to minus PB prime minus PB, that is, PA prime plus PB prime is equal to PB plus PA, which shows that the total final momentum of the isolated system equals its initial momentum. This is true whether the collision is elastic or inelastic. Circular motion. Acceleration of a body moving in a circle of radius r with uniform speed v is v square upon r directed towards the center. According to the second law, the force F providing this acceleration is F is equal to mv square upon r, where m is the mass of the body. This force directed towards the center is called the centripetal force. For a stone rotated in a circle by a string, motion of a car on a level road, motion of a car on a level road taking a circular turn. Three forces act on the car. 1. The weight of the car, mg. 2. Normal reaction, N. 3. Frictional force, F. As there is no acceleration in the vertical direction, N minus mg is equal to 0. N is equal to mg. The centripetal force required for circular motion is along the surface of the road and is provided by the component of the contact force between the road and the car tires along the surface. This, by definition, is the frictional force. Note that the static friction opposes the impending motion of the car moving away from the circle. Using equations, Fs is less than or equal to mu s n and F is equal to mv square upon r. F is less than or equal to mu Sn is equal to mv square upon r. Mu Sn is equal to mv square upon r. Mu Snr upon m is equal to v square, where n is equal to mg. V square is equal to mu s mgr upon m. V square is equal to mu s gr. V is equal to under root mu s gr, which is independent of the mass of the car. This shows that for a given value of mu s and r, there is a maximum speed of circular motion of the car possible, namely V max is equal to under root mu s gr. Motion of a car on a banked road. We can reduce the contribution of friction to the circular motion of the car if the road is banked. Since there is no acceleration along the vertical direction, the net force along this direction must be zero. Hence, n cos theta is equal to mg plus f sin theta. The centripetal force is provided by the horizontal components of n and f. N sin theta plus f cos theta is equal to mv square upon r, but f is less than or equal to mu Sn. So, to obtain V max, we put f is equal to mu Sn. Then, equation n cos theta is equal to mg plus f sin theta becomes n cos theta is equal to mg plus mu Sn sin theta. Putting the value of f in equation, n sin theta plus f cos theta is equal to mv square upon r, we get n sin theta plus mu s n cos theta is equal to mv square upon r. From equation n cos theta is equal to mg plus mu s n sin theta, we get n is equal to mg upon cos theta minus mu s sin theta. Putting value of n in equation n sin theta plus mu s n cos theta is equal to mv square upon r, we get v square is equal to rg into sin theta plus mu s cos theta upon cos theta minus mu s sin theta. Changing sin theta and cos theta in terms of tan theta, we get V max is equal to under root rg into mu s plus tan theta upon 1 minus mu s tan theta. This expression shows that the maximum possible speed of a car on a banked road is greater than that on the flat road. For mu s is equal to 0 in equation, V max is equal to under root rg into mu s plus tan theta upon 1 minus mu s tan theta, we get V0 is equal to under root rg tan theta. At this speed, frictional force is not needed at all to provide the necessary centripetal force. Driving at this speed on a bank road will cause little wear and tear of the tires. Friction. Let us take the example of a body of mass m at rest on a horizontal table. The force of gravity, mg, is cancelled by the normal reaction force, N, of the table. Now, suppose a force F is applied horizontally to the body. We know from experience that a small applied force may not be enough to move the body. But if the applied force F were the only external force on the body, it must move with the acceleration F upon m, however small. Clearly, the body remains at rest because some other force comes into play in the horizontal direction and opposes the applied force F. Resulting in zero net force on the body. This force Fs, parallel to the surface of the body, in contact with the floor, is known as frictional force or simply friction. The subscript stands for static friction to distinguish it from kinetic friction, Fk. Note that static friction does not exist by itself. When there is no applied force, there is no static friction. It comes into play the moment there is an applied force. As the applied force F increases, Fs also increases, remaining equal and opposite to the applied force up to a certain limit, keeping the body at rest. Hence, it is called static friction. Static friction. Static friction opposes impending motion. The term impending motion means motion that would take place but does not usually take place under the applied force if friction were absent. As the applied force exceeds a certain limit, the body begins to move. It is found experimentally that the limiting value of static friction, Fs max, is independent of the area of contact and varies with the normal force N approximately as Fs max is equal to mu Sn, where mu s is a constant of proportionality. Depending only on the nature of the surfaces in contact. The constant mu s is called the coefficient of static friction. If the applied force F exceeds Fs max, the body begins to slide on the surface. It is found experimentally that when relative motion has started, the frictional force decreases from the static maximum value, Fs max. Frictional force that opposes relative motion between surfaces in contact is called kinetic or sliding friction and is denoted by Fk. It satisfies a law similar to that for static friction. Fk is equal to mu Kn. Mu K, the coefficient of kinetic friction, depends only on the surfaces in contact. As mentioned above, experiments show that mu k is less than mu s. When relative motion has begun, the acceleration of the body, according to the second law, is A is equal to F upon m. A is equal to F minus Fk upon m. For a body moving with constant velocity, that is, A is equal to 0, 0 is equal to F minus Fk upon m. F is equal to Fk. If the applied force F on the body is removed, its acceleration A is equal to Fk upon m. And the body eventually comes to a stop. Example of static friction. Friction, by definition, is the component of contact force parallel to the surfaces in contact, which opposes impending or actual relative motion between the two surfaces. Note that it is not motion but relative motion that the frictional force opposes. Consider a box lying on the floor of a bus that is accelerating. If the box is stationary relative to the bus, it is in fact accelerating along with the bus. A question to think about is, what forces cause the acceleration of the box? Clearly, the only conceivable force in the horizontal direction is the force of friction. If there were no friction, the floor of the bus would slip by and the box would remain at its initial position due to inertia and hit the backside of the bus. This impending relative motion is opposed by the static friction Fs. Static friction provides the same acceleration to the box as that of the bus, keeping it stationary relative to the bus. Rolling friction. A body like a ring or a sphere rolling without slipping over a horizontal plane will suffer no friction in principle. At every instant, there is just one point of contact between the body and the plane. And this point has no motion relative to the plane. In this ideal situation, kinetic or static friction is 0. And the body should continue to roll with constant velocity. We know in practice this will not happen, and some resistance to motion or rolling friction does occur. That is, to keep the body rolling, some applied force is needed. For the same weight, rolling friction is much smaller, even by 2 or 3 orders of magnitude, than static or sliding friction. This is the reason why discovery of the wheel has been the major milestone in human history. Rolling friction again has a complex origin. though somewhat different from that of static and sliding friction. During rolling, the surfaces in contact get momentarily deformed a little. And this results in a finite area, not a point of the body, being in contact with the surface. The net effect is that the component of the contact force parallel to the surface opposes motion. Friction as necessary evil. We often regard friction as something undesirable. In many situations, like in a machine with different moving parts, friction does have a negative role. It opposes relative motion and thereby dissipates power in the form of heat, etc. Lubricants are a way of reducing kinetic friction in a machine. Another way is to use ball bearings between two moving parts of a machine. Since the rolling friction between ball bearings and the surfaces in contact is very small, power dissipation is reduced. A thin cushion of air maintained between solid surfaces in relative motion is another effective way of reducing friction. In many practical situations, however, friction is critically needed. Kinetic friction that dissipates power is nevertheless important for quickly stopping relative motion. It is made use of by brakes in machines and automobiles. Similarly, static friction is important in daily life. We are able to walk because of friction. On an ordinary road, the friction between the tires and the road provides the necessary external force to accelerate the car.